Oh boy. Okay, sorry, I just realized I didn't give you a break between the classes. Usually I start at 4 after Phil's finished doing the camera stuff, but I got a bit nervous and I just started right away. So it's still not yet 4, so you still have time to take a break. I just got a bit nervous. There's a couple people observing this class, so if you're wondering why Jordan, your calculus teacher, and Mary Power from the Center for Teaching Excellence is here, there's just going to be a couple people observing this class today. So sorry for sorry for starting. So this warm-up page was supposed to be up there, but you didn't have to start working on it yet. So we'll start at 4 o'clock. I'll give you guys another 2 minutes to have your break between classes. Still about 1 minute to 4, so I'll give you a bit more of a break. Okay, since it's 4 o'clock, once again, sorry for starting the warm-up so early. Usually I'm not supposed to start that until 4, but everyone's had a chance to look at this warm-up problem. Does anyone think that they've made some progress on it? Very good. Okay, I'll cover this in a minute. I'm just going to first start with the objectives for today's lesson. I'm going to first talk about the results from Monday's survey, the survey from 2 days ago. Thank you all for filling it out. And then we're going to go over this number theory proof, which was the warm-up slide. And then we're going to do another warm-up, which is a GCD proof. And then I'm going to try to give you some motivation for the next chapter. And that motivation should hopefully lead into a very fun modular arithmetic proof. A proof that I think is very fun, at least in my opinion, it's really fun. Okay? So with that, I'll start with the results from the survey. There was 2 questions from the survey that I was particularly concerned about. I really wanted your feedback on this. One was the playing music before classes, because that's something I used to do when I was teaching at Oxford, but it's been a long time since I've been in Waterloo, and this is maybe a bit unconventional to be playing music at the beginning of class. I do that to stimulate everyone after a tiring day of lots of classes. Then I was hoping it might stimulate people, and it turned out 98% of the people say that they want me to continue playing the music. So I said, would you prefer I don't play any music at all? 79 people said false. 2 people said true, but one of those people, actually in question 4, recommended a bunch of songs that they want me to play at the beginning of classes. So they might have just got the true or false wrong. So it turns out 98% of the class, at least, does want me to continue playing music. So I can continue doing that. Thank you very much for the feedback. The other thing I'm often worried about is that my voice is too loud, because I'm used to giving talks at research conferences in rooms much bigger than this. And I was very worried about my volume being too loud. So I asked to give me a 1 if I'm too loud and a 10 if I'm at perfect volume. So about 92% of the people said that I was either at perfect volume or 9 out of 10. But of course, there are some people that find me too loud, which was what I was worried about. And so what I can do about that, I could try to speak a little bit less loud. There's also 58 and 16 people giving me 10 out of 10, 9 out of 10 there. So if you do think I'm too loud, another option could be to sit maybe 1 or 2 rows further back, because this is a minority here. Okay, so, but thank you very much for filling in these 11 questions I gave, and I will take a look at everything you wrote. Okay, I want to take it all into account for my future lectures. Okay, Now for the warm-up question. So the first part, it asked to prove that n factorial plus 3 is not prime, as long as n is greater than or equal to 3. Okay? The second part was a bit more complicated. We're proving that for every prime number k, we can find k consecutive non-primes. So k equals 2 is a prime number. We can find 2 consecutive numbers, 8 and 9. 8 is non-prime, 9 is non-prime. Okay, and we're going to prove that we can do that even if we're not just dealing with k equals 2, but also k equals 3, k equals 5, and so on. So, this proof, first of all, if you're wondering why am I asking you that was actually a Math 135 question from fall 2007. And this was question 8A and B. You can see it's the same question. I just blew it up a little bit because I worry if some people might not be able to read it in this font. But that was a question from 2007, from the 2007 version of Math 135. So it was there to give you some practice for the exams. So those of you that made some progress on this proof, prove that n factorial plus 3 is not prime. How many people made some progress? Okay. So does someone want to say what they did? Paige?
Well, we know that n is bigger than 3, so we can write n factorial 1 times 2 times 3 times every other integer until n. And then since 3 is included in that, we know that 3 divides n factorial, and 3 also divides 3. So by DIC, we can conclude that 3 divides n factorial plus 3.
Very good. That's exactly what I have on my next slide. I'm just going to go through it for the rest of the class in case that was too fast for anyone. So I prepared this slide assuming the worst case scenario where no one's able to figure out the proof. So I was going to ask the class a question. If n factorial plus 3 is not prime, then can you tell me a prime number other than itself that factors it? Okay, if it's not prime, then tell me one number which is not itself that factors it, other than 1 or itself. And often people will then think, okay, 3 factors n factorial plus 3. But I also know how many people didn't think of that? There's probably some people, yeah. So I didn't think of that right away, and I actually went through a more systematic procedure to try to prove this. And I know on the survey also a lot of people said they want me not to just give the proofs, but to also talk about how I think my way through the proof, my thought process to do the proof. So here's the thought process. So first, I try the smallest possible prime factor. I want to find a factor of n factorial plus 3. Okay, I don't start with a prime number like 29 or 31 or something big. I start with the smallest and simplest prime number, 2. Does 2 divide n factorial plus 3? You can yell it out? No, okay. And yeah, why is that, Eric?
Because no matter if it's even or odd, it'll always result in an odd number when you take the n factorial plus 3, because, yeah, I don't know, that's how I started doing the proof, because I checked it, did like the case where it was even or odd, and then I checked what it would result in every time it results in an odd number.
Oh, every time you plugged it into your calculator, you got an odd number?
Yeah.
Okay, but how would you prove it on an exam? You can't just say that for the first 10 numbers I checked, it worked. Mia?
Well, n factorial, like they said, it's 1 times 2 times 3 times the next numbers until n, and that's always going to include 2 as a factor, so n factorial is always included. And then if you add an odd number, then it's odd, so 2 will not divide it.
Excellent. Yeah, so I'm just going to repeat it in case anyone wasn't able to hear that. She said that n factorial, it's something times 3 times 2 times 1. It has a 2 in there. It's written as a product of numbers including 2. So 2 is a factor of n factorial. That means n factorial is always an even number as long as n is bigger than or equal to 2. And then you have an even number plus an odd number. So n factorial plus 3 is always odd. Okay? So that didn't work. 2 doesn't divide n factorial plus 3. Now let's try 3. 3 divides n factorial plus 3. That's the question. The answer is yes, because again, n is greater than or equal to 3, so I can write n as something times 3 times 2 times 1. So Paige got that immediately, so 3 divides n factorial. 3 also divides 3, so 3 divides n factorial plus 3. Why?
DIC.
DIC, divisibility of integer combinations. Okay, good. So now we know that there's a factor other than 1 or itself, so n factorial plus 3 is not prime. The second question, prove that for every prime k, we can find k consecutive non-primes. How many people made some progress on this one? This one's a bit tougher, isn't it? Okay, I also got stuck when I started this, and I think if they didn't give us part A, then I wouldn't have known what to do. But because they gave us part A and part B, usually there's a reason why they do that, why this is a part B of question 8. The part A, let's try to use part A, okay? So no one made any progress with this one? Okay, let's go through it. So 3 divides n factorial plus 3. We already proved that. And I can also use the same type of reasoning to say that r divides r factorial plus r. As long as n is larger than or equal to r, then any number. 5 divides 5 factorial plus 5, right? Because 5 factorial contains 5 in it. And then, so 5 divides 5 factorial, because 5 divides 5 times 4 times 3 times 2. 5 also divides itself. And so again, r divides r factorial plus r. And it doesn't matter if r is equal to 3, 4, 5, 6, okay? So I'm going to make a claim now. Oh, Paige?
Is it supposed to be R factorial or N factorial?
I think I meant to say r factorial here. Good. Yeah, no one in the last class pointed that. No, that's supposed to say n. So this is n factorial plus 3. Yeah, this was supposed to say n factorial plus r. So no one said that in the last class. Usually by the time I do this class, the previous classes told me if I've made a typo. But that's a good point. So this is the same proof as what we did for 3 divides n factorial plus 3, except we have r instead of 3. Okay? Does anyone have any questions? Sorry, I might have thrown you off a little bit there. But I think also r also divides r factorial plus r. That's also true. And we're actually going to use that. So r divides n factorial plus 3 as long as n is larger than or equal to r, but it also divides r factorial plus r. And now I'm going to make a claim. K consecutive non-primes, I'm going to write it like this, okay? I've let r equal to k plus 1 here. And all of these numbers here, they're all non-primes. The reason they're not prime, this one is divisible by 2, by the argument we just made. This one is divisible by 3. This one is divisible by 4. This one is divisible by k plus 1. And how many numbers do I have here? I have something plus 2, something plus 3, all the way up to something plus k plus 1. How many numbers do I have? Pardon me? K. Yeah, there's k of them, because I have something plus 2, something plus 3, something plus 4, all the way up to something plus k plus 1. So there's k numbers there, and these are all consecutive numbers, and they're all not prime. This one's divisible by 2, this one's divisible by 3, and so on. Okay? We can also test this. Okay, for k equals 2, we plug numbers into this formula, so we have 3 factorial plus 2, and 3 factorial plus 3. 3 factorial is 6, so we have 6 plus 2, that's 8. 6 plus 3, that's 9. So we have 8 and 9. Those are 2 non-prime numbers which are consecutive. Then we have k equals 3. Consecutive non-primes, they're going to be 3 plus 1 factorial plus 2, 3 plus 1 factorial plus 3, 3 plus 1 factorial plus 4. So we have 4 factorial, that's 24. 24 plus 2, 24 plus 3, 24 plus 4. Okay? K equals 5. We can try this one too. K plus 1 is 6. 6 factorial plus 2, 6 factorial plus 3, 6 factorial plus 6. What's 6 factorial?
720.
720. Good. So we have 720 plus 2, 720 plus 3, 720 plus 4. And these ones are even numbers. So 722, 724, 726, those are all even numbers, so those are not prime. And 725 ends in a 5, so that's divisible by 5. That's also not prime. And 723, that equals 3 times 241. You could have also discovered that by adding up the digits and seeing if it divides, if 3 divides it. So here we have 5 consecutive non-prime numbers. Okay, and this formula, that formula works. It's just a warm-up, so this is a proof outline. If you don't feel comfortable with this proof, you can try to spend some time writing it out in your own words. But that's the proof idea here. Okay, and I know a lot of people have been asking me, how do I approach these proof problems? I don't know what to do. Has anyone seen a question like this before? N factorial plus 3 prove that it's not prime? No one's ever seen a question like that before? Okay, there was one student in the last class, he said that he's seen questions like that on a math contest. But for the most part, we're giving you questions that we believe you would be able to prove using the theorems in the course notes, but you've never seen any question like this before. We're asking you to think in a way that you might not have had experience with before. Okay, so it's a little bit different. There's no step-by-step procedure that always works. Something like the product rule in calculus, if you have two functions, you want the derivative of the product, then you do the derivative of each function and you use a formula to calculate the derivative of the product. And there's a step-by-step procedure, and as long as you follow that step-by-step procedure, you get the answer. For proofs in number theory, it doesn't quite work that way. The proof for n factorial plus 3, we did it in a certain way. For a different proof, to prove that something else is not prime, then you might have to prove it by contradiction or by induction. There's no step-by-step procedure. And I really love this quote, because when we're talking about the fact that there's no step-by-step procedure, I love this quote, okay? O king, for traveling over the country there are royal roads and roads for common citizens, but in geometry there is one road for all. This was told to Alexander the Great. He was told this when he asked Menaechmus for a shortcut to learning geometry 2,350 years ago. Okay, so kings, they don't have to wait in line to use the bathroom, right? They don't have to wait in traffic on the 401. They can just take their private jet, right? So they have shortcuts to a lot of things, but if they want to learn geometry, there's no shortcut. Okay, so there's no shortcut here. If you practice proofs, you will get better. So the more you practice, the more you've seen some of these proof strategies, the more familiar you will be with questions we'll give you on the exam. Okay, so with that, I will put one more warm-up question up. This is a question from the Fall 2000 final for Math 135, and it's probably too small for you to see here, so I've blown it up a little bit, okay? But you can find this question on the MathSoc exam bank, Fall 2000, Math 135 final. So, prove that if GCD of A and B equals 1, then GCD of A plus B and AB equals 1. Okay? Did I present this at the end of last class? This question? Okay. So, this question, you don't need a lot of time to start it because, well, okay, how many people think they know how to start this proof? Philip?
Bézou's lemma.
Bézou's identity, or Bézou's lemma, as it's sometimes called. Yeah, so I told you before, well, we went through all the proofs in the course notes, almost all of them, they started with Bézou's identity, so it's not a bad idea to start with that. And this time actually we'll give you a little bit of a proof strategy for GCD problems. So the Bézou identity is a good place to start when the GCD is in the hypothesis. Here we have a hypothesis and a conclusion. So there's a GCD in the hypothesis, so it's a good strategy to use Bézou's identity. Now, we can also use GCD with remainders when the GCD depend on when the terms in the GCD depend on each other. So if we want to do GCD of A of X, where A depends on X, then you might want to do GCD with remainders. GCD characterization theorem, that's good to use when the GCD is in the conclusion. Okay? Now in this case, we do have a GCD in the conclusion. Okay? So how would you use the characterization theorem here? The GCD characterization theorem. Philip?
If we find integers such that x times a plus b plus y times ab equals 1, therefore 1 is the GCD since 1 divides both of those.
Exactly, yeah. So if you remember the GCD characterization theorem, it tells us if we have the GCD equals D, we have to check if D divides A plus B, and D divides AB, and D is greater than or equal to 0. D is greater than or equal to 0, and we have to check that A plus B times an integer plus AB times another integer equals the GCD. And that's the GCD characterization theorem. So if you want to prove that the GCD equals something, you use the GCD characterization theorem. That's precisely what it's for. It's called the GCD characterization theorem. But in this case, because we have that the GCD equals 1, we basically end up with what Philip just said, which was Bézou's identity. We just ended up with Bézou's identity. We just ended up with A plus B times X plus AB times Y equals 1. So that's also good, that's reassuring to know that this strategy is a good one. The third step in this strategy is to use Bézou's identity, which that's why Bézou's identity was the first thing we recommended. Some of the other things even reduced to Bézou's identity in special cases. Okay, now there's the definition of GCD. That's something you can use when nothing else seems to work. Okay? Are there any other GCD theorems we might want to use if we want to prove something about GCDs?
I mean,
Yeah?
there would be more specific cases, right? Like instead of GCD-CT, when you see that there's one, you might as well think of the co-primeness characterization theorem.
Okay, so co-primeness characterization theorem is to...
a more specific case of the GCD-CT, it is the co-primeness.
yeah, so within GCD-CT, there's more specific cases within there. But all of those cases can be generalized under one umbrella.
Or I think there's another one.
Yeah, there is one more.
CCD, GCD.
Pardon me?
CCD, GCD, the common divisor divides. CDD, GCD, common divisor divides greatest common divisor.
Yeah, in this case, we don't want to prove anything about the common divisors themselves. We just want to prove that a certain GCD
I thought you asked
equals another one.
Is there any other strategy?
Yeah, but there is one more. There is one more GCD theorem. GCD PF. You remember what that stands for? GCD prime factorization. So that's a theorem in the course notes. And when would you use that? If this is what you use when nothing else seems to work, when would you use GCD PF? Okay, my advice is to use that. Well, GCD PF, that's good when you're desperate. Okay, when nothing else works and you're desperate, you have 10 minutes left in the exam, GCD prime factorization might work when nothing else works. Okay, but I would not recommend to use this first. I would recommend to use this strategy. The reason is GCD PF, you have to find a prime factorization. Even writing that out will take some time. You have to do P1 to the power A1 times P2 to the power A2 times all the way up to Pn to the power An, and then you're doing that for each number in the GCD proof, and it can take a long time. Okay, so it's good to know, but if you follow this procedure for most GCD proofs, you might get the proof quicker. So we will use Bézou's identity, as I think Philip suggested. So we have that the GCD of A and B equals 1. Okay, that means AX plus BY equals 1 by Bézou's identity. Okay, now what else should we do? We want to prove something about the GCD of A plus B and A times B. Here we don't have any A times B. So what do you think we might want to do? Grayson?
Are we going to add and subtract some term containing A times B times something else?
Okay, that's one thing we could do. That's one thing we could do. There's something we can do to get from here to an expression that has a product of A and B without, because then you don't even know what you want to, oh, I don't know, the timer. Versano, you were going to say something?
I was just going to say maybe multiply everything by B.
Okay, you could multiply everything by B and you'd have a B squared there. And since we're talking about multiplying, so if you multiply everything by B, you'll get a B on this side. How can we multiply this in such a way that we'll still have a 1? But we want to multiply by something such that we'll still have a 1 there. Versano?
B over B then?
Okay, so multiply by 1. That's a good idea, but let's let Grayson answer as well.
square both sides.
Square both sides. That happens to be what I did in my proof. So I squared both sides. So here I'm multiplying it by itself, and so the 1 stays where it is, because we know we're going to need that, because we're doing a GCD co-primeness proof. And then we got the AB that we wanted. Okay? And then now what is it that we want to prove? Remember what it is that we want to prove. We want to prove that the GCD of AB and A plus B equals 1. How would we do that? What's the theorem that tells us how to... Someone already mentioned it once, but what's the theorem that tells us how to characterize whether or not two numbers are coprime?
CCT. Yeah,
Arnav?
CCT, right?
CCT, that's coprimeness characterization theorem, right? So if we want to check whether two numbers are coprime, we can use the coprimeness characterization theorem. That's precisely what it's for. So this states that GCD of A plus B and AB equals 1 if and only if A plus B times P plus AB times Q equals 1 for some integers P and Q. Okay, so we want to prove that this equals 1, and this will definitely equal 1 if we can prove this, because this if and only if goes both ways. It means that if we can find the P and Q such that this expression is satisfied, then we know that GCD of A plus B and AB equals 1. So we just want to find this P and Q, and we can do that by rearranging this equation we have right there. We rearrange it, and we get A plus B times this, plus A times B times that equals 1. So we found our P and the Q, and because that P and the Q, those are integers, then by the coprimeness characterization theorem, we know that GCD of A plus B and AB equals 1. Okay? Does anyone have any questions before I move on? Grayson?
I think you should have a 2abxy up near the top of the slide.
Yeah.
Oh yeah, so yeah, that's an error I have there. That should be a 2.
But it
That's
looks like
right,
you
yeah.
fixed it from the bottom line.
Yeah, so that's why I had a 2xy here and only a 1xy there. Thank you for pointing that out. Yeah, sorry about that. No one pointed that out in the last class either. Okay, so does anyone have any questions about this proof though? It's quite, it's okay. It's just a few steps, right? Once you start with Bezout's identity, and you recognize that we want to prove something about A times B, and we only have A and B added in some way. We don't have any A times B. You can square both sides. That doesn't change the right side, but it gives us this AB that we wanted. Then we just have to rearrange it until we can use this coprimeness characterization theorem. Okay, so since I'm not seeing any questions about this, I'll move on to the next slide. I want to motivate a little bit. Oh, Arnav?
Yeah, like, what did you manipulate there? Like, I sort of lost it after the CCT. Like, A plus B, because if you're using the CCT, does that mean you assume values for P and Q?
No, so we're not assuming any values of P and Q. For the CCT, it works both ways, right? So the CCT states that A plus B and AB are coprime if we can, if and only if, so that means it's true if we can find a P and Q such that this expression is satisfied. And here we found the P and the Q. We found the P and the Q, and it worked. There's some algebra, there's some steps you might want to take to finish this, but it's only meant to be a warm-up. I'm giving you the proof outline, and the remainder of it, if you want to double-check all the arithmetic, that's something you can do afterwards if you want. Okay, so I think at this point in time, when I was taking Math 135, I needed a little bit of motivation to understand why we're doing all this, okay? We have proven in this class, we proved that the GCD of 22a plus 7 and 3a plus 1 is 1, okay? But I don't think I've seen, has any of you seen a mathematical problem where you had to deal with 22a plus 7 and 3a plus 1 at the same time? For Sano?
Might have been on a Mobius quiz.
It might have been on a Mobius quiz. What about in real life?
No.
No, okay. And in GCD, so we just proved just now that GCD of A and B equals 1 implies that GCD of AB and A plus B equals 1. And we asked you on the assignment to prove that GCD of A and B equals 1 implies that GCD of AN plus U and BN plus V equals 1. We also asked you on a midterm to prove that if A divides 2B plus C, then A doesn't divide B minus 2D, or A does divide C plus 4D. Okay, so there's some complicated expressions involving divisibility and GCDs, and we're asking you to prove them. But you might wonder, like I did when I was a Math 135 student, why do we need to know that the GCD of this complicated expression and this other complicated expression is 1 or 2 or whatever it is? Okay, and I think at the same time as taking this class, you're taking calculus. And in calculus, the motivation is quite clear. For example, optimize the profit based on the revenue function and the cost function. Okay, how many items do I have to sell? If I have to produce too many of these items, then the cost might be too much. But if I don't sell enough of them, I'm not making enough money back. So optimizing profit, rate of change. Okay, acceleration, it's the derivative of velocity, right? So how much deceleration does the self-driving car need to stop before the stop sign? Rate of change of COVID growth. Okay, in February 2020, there was 1 case, then there was 2 cases, then there was 4 cases, then there was 8 cases, then 400 cases. And I might want to know, how quickly is it changing? Is it growing exponentially or quadratically? I might want to predict how many cases are there going to be in December. If I want to see my grandmother for Christmas, then should I buy the flight now? Or should I not buy the flight because there's going to be 2 million cases per day in that town? Okay, so we want to know the rates of change of things. I never needed anyone to tell me why we're learning calculus. Right away I see there's some function, I can get the slope, I can know about the growth of that function. It was always intuitive to me why we learn calculus. For number theory and Math 135, it was a little bit harder for me to grasp. For example, we could prove this. This is what we proved on the midterm, except I've replaced C with GCD of U and V and D with GCD of E and F. So we have that A divides 2B plus the GCD of U and V. That implies that A doesn't divide B minus 2 GCD of E and F, or A divides GCD of U and V plus 4 times the GCD of E and F. Now, why would we need to do that? Can anyone see why we would care about that? Probably not, but there is actually some good reason for this, which I'm going to get to in a second. I'm also just going to motivate this with one more slide. I'm just going to say that when I was an undergrad here at Waterloo, a friend of mine was doing a research project with a professor here in number theory. And the project was about checking to see whether or not any odd triperfect numbers exist, or finding odd triperfect numbers. So a triperfect number is a number where the sum of all divisors of n is 3n. And apparently, no one's ever found any odd numbers that satisfy this property. Okay? If I look up triperfect numbers, I find that no one's ever found an odd triperfect number before. But if it does exist, it's larger than 10 to the power 70. Okay, and my friend that was doing his undergrad research project, he was using a $200,000 supercomputer, searching through all sorts of numbers, searching through every number up to 10 to the 50 or something like that. And he didn't find any odd triperfect numbers. And I guess a little bit later than that, it's now been increased in this publication to 10 to the 70. Okay, and I wondered, he was getting paid to look for odd triperfect numbers, something I'd never heard of. And in my physics friends, they were studying black holes and stuff. Okay, and I also had friends in chemistry. Linda Nazar, she's in University of Waterloo. She got the Order of Canada for her research in lithium-ion batteries. Okay, so our phones are using batteries that can last longer than what they did 25 years ago when they're using alkaline batteries. So I always wondered what the purpose of this was. And it turns out, we can also ask, why does n factorial plus 3, why does it matter whether it's prime or not? Okay, it's just a number. Why does it matter if it's prime or not? And whether or not numbers with certain properties exist, that actually happens to be at the heart of cryptography. Okay? So for example, if I have a picture of myself that I don't want any of you to see, or if I'm sending a private message to a family member, okay, and it has some private information about financial information or something that I don't want others to see, I can encode it with secret code such that you would have to solve a puzzle to read the message. And that puzzle can be so difficult that it's not one of those puzzles that you can do by hand, but you need to do calculations. In order to solve that puzzle, you need to do calculations that require computers to do really big arithmetic. Okay? And furthermore, my computers might have the puzzle pieces and yours don't. So I know that some certain numbers with certain properties exist, and I have those numbers on my computers and on my family computers. They're secret keys. And your computer doesn't have those numbers, and you don't even know whether or not those numbers exist. Okay? So chapter 9 will be all about RSA cryptography, a particular type of cryptography named after Rivest, Shamir, and Edelman. Okay? So chapter 9 will be all about cryptography. You're going to learn how we can use number theory to actually secure information. But we have to teach you chapter 8 first, because this RSA cryptography scheme, it's going to rely on all of the GCD theorems that we've been using so far, plus Fermat's little theorem, Chinese remainder theorem, and a few more. Okay, so that's coming up next. And I just wanted to show, this is, if you visit any website in a browser, okay, how many people have seen this lock, this security? You've seen that before? Okay, if I click on that, it says connection is secure. I can click and find out more. It says certificate is valid. And it says right here, I'm sorry, some people might not be able to see this. I tried to see if I could make this bigger. But, so right here it says SHA 256 RSA. That's using the RSA algorithm, which we're going to be teaching you a week from now. And there's also some other numbers here, ECC, that's elliptic curve. There's other things here like the domain name server, certificate policy. You remember we taught you about certificate of correctness? What's certificate of correctness? Versano?
It was Bezout's lemma such that there exists integers s and t when multiplied and then added to your original GCD, they equal the greatest common divisor.
Yeah, and what in that case with the S and T, what
AS plus BT is equal to D, and D is the greatest common divisor of A and B.
Okay, in that case, the S and the T, that's your certificate of correctness. Okay, and then there's other things here like digital signatures and things like that. So that understanding how the security works, even on our own browsers, that's going to be something that I hope by next week you're all going to be able to understand. Okay, also if you're more interested in cryptography, there's CO courses, the CO 485, for example, Mathematics of Cryptography offered here. This requires a bunch of PMath courses. And all of those PMath courses require Math 235. Math 235 requires Math 136. And can you guess what 136 requires? 135. Okay. Alternatively, there's an applied cryptography course, 487, and that requires Math 135 and Stat 230. So again, you need to know Math 135. I think I put here, if you're interested in this stuff, this is on the UW course calendar. You can find applied cryptography, that's a course, and it says prerequisite Math 135. Okay, now there's an even, I wanted to pay homage to a University of Waterloo professor. You can see he lived in Kitchener, Ontario until his death. And he was in the combinatorics and optimization department, Bill Tutt. During Second World War, he made brilliant and fundamental advances in cryptoanalysis of the Lorenz cipher, a major Nazi German cipher system which was used for top secret communications. So to be able to break codes, to learn what the enemies were thinking or what they were communicating to each other, he used mathematics, basically. He used number theory to help understand how that crypto system worked. And if any of you, have you ever been around the Davis Center building? There's a street on the University of Waterloo campus named after him. It's called William Tutt Way. Has anyone seen that one? Okay, a couple people in the, oh yeah, you've seen it, Jimmy. Okay, good. Okay, now something else. Cryptography, I already knew before taking Math 135 that cryptography was going to be one of the applications. Everyone that's taken Math 135 knows that, so I wasn't surprised about that. There's actually one more application of Math 135 that I want to talk about doing these GCD proofs. And that's, I think, even more powerful than cryptography. And that's the way your computer calculates things very quickly, okay? How it does fast computations. Okay? And the course notes don't talk about this. I only learned this once I took CS 487, Introduction to Symbolic Computation. So all these GCD theorems, they all have analogs. We're teaching them for integers. We also have polynomial versions of those theorems. Okay? And then if I want to multiply two huge numbers together, huge, you might wonder, why does it take so long to upload my assignment to CrowdMark, but the computer can multiply these huge numbers together so fast. Okay, now imagine you have a number, you have a polynomial, it's a1 x1 plus a2 x2, a1 x to the 1 plus a2 x to the 2, all the way up to a15 x to the 15, and you multiply that by another polynomial. Okay, now if you plug in x equals 5, you get a huge number, right? You plug in x equals 5, you get something that's bigger than a15 times x to the 15. Okay, you can get big numbers this way. And if you want to multiply two polynomials that are order 15, that's not too hard, right? There's 15, 16 terms here, 15, 16 terms here. It's not that hard for the computer to do. Now you multiply these two numbers, and you multiply these two polynomials, and you get a number. You get the product is some other polynomial, and then you plug in x equals 2, you can get the product of two huge numbers that way. And that's symbolic computation. So numerical computation is a special case of that. You plug in numbers at the beginning, and you're just multiplying the numbers numerically. Here you're doing symbolic computation. You're working with symbols, and then you plug in the numbers later. And I took this course a long time ago. The current Dean of Mathematics, Mark Giesbrecht, he was actually the instructor for that course when I took it. And so it requires CS 234 or CS 240, which require Math 136, which requires Math 135. And you'll see if you look at the course notes for that course, it's GCD theorems all over the place. Okay, another very quick piece of motivation here. I'm going to show you an 18-second video here. I don't even need that one. Okay, so how do I turn up the volume? Now this is a video, this is a former student of mine actually, and he's asked a question. This video became viral because he answered the question so quickly. Okay?
What day of the week will it be 100 days after Monday?
Modern Wednesday. How did you know that?
So, what did he say at the end? Modular arithmetic, right? So, just for anyone that wasn't able to pick up on what they said there, he was asked, what day of the week will it be 100 days from now? What day will it be 100 days from now? And he said right away, he said it's going to be Wednesday. And then he was asked, how did you know that? And he said, modular arithmetic. Okay, so he was asked, how did you know that? The answer is modular arithmetic. Okay, and you've probably seen, if you did the practice exams, you've seen this mod everywhere, right? So, who's ready to learn modular arithmetic? Few people? Yeah? Okay, so let's do a little bit of modular arithmetic. So 28 is congruent to 0 mod 7. That's because 0 is the remainder when we divide 28 by 7. Okay? Now I'm just going to show you something quickly. We're going to prove a lot of theorems about modular arithmetic on Friday. But for now I'm going to show you something quickly. So 28, we subtract 1 from both sides. We get the 28 minus 1, that's 27. 27 is congruent to minus 1 mod 7. Okay? And so I'm going to show you now how to basically answer a question 100 times harder than what my former student answered in that quiz show. Okay? Instead of asking you what day of the week will it be 100 days from now, what if I asked you what day of the week will it be 3 to the power 47 days from now? Okay, we can actually do this in just a couple steps without a calculator. Okay, 47, that's a prime number, so we're going to split it up into 2 times 45. 2 is also a prime number, but it's smaller and more manageable. 45, that's also a number we can split up. We can split that up into 3 times 15. Okay, so we have now 3 squared times 3 cubed to the power 15 mod 7. Now, we already proved that 27 is minus 1 mod 7, right? So we also know 9. What's 9 mod 7? 2. Okay. So we have 2 times negative 1 to the power 15. What's negative 1 to the power 15? Negative 1. Excellent. So we have negative 1 times 2. That's minus 2 mod 7. Okay? And then just to rearrange it, to write it like we did at the beginning, we add 2 to both sides. We get 3 to the power 47 plus 2 is congruent to 0 mod 7. That means 7 divides 3 to the power 47 plus 2. You can also check in Wolfram Alpha. You check that this is an integer. That's an integer. That means that when you take this, you divide it by 7, you get an integer, so it's divisible by 7. Okay? So we were able to do this in just a few steps, and no one needed a calculator, right? So if now you're on a quiz show and someone asks, what day of the week will it be? 3 to the power of 47 days from now. What's the answer? Versano?
The day is currently plus 2 more days.
Plus 2 more days? Okay, how many people think plus 2 more days? Okay, what do others think if you don't think it's 2 more? Yeah, Philip?
Whatever day of the week it was 2 days ago.
2 days ago. Okay, so how many people think it's today plus 2 more days? And how many people think it's today minus 2 more days? Okay, so that's right, because in the case where we're asked, what day of the week is it 100 days from now? Okay, 100, if you divide 100 by 7, you'll get 98 plus 2. So 7 goes into 70 10 times, and then it goes into 98 14 times. That's another 28 you're adding to the 70. I'll write this on the board to make it clearer. Okay, if I have 7 times 10, I get 70. If I do 7 times 4, I get 28. And now I have, if I add these two, I get 98. Can I put any more 7s into there? And can I put any more 7s into 100? No more left, right? And the remainder, so if I have 100 and I divide that by 7, that's equal to 7 times, in this case, 14, plus what? What's the remainder? 2. Positive 2, right? So in that case, we would have 100 is congruent to 2 mod 7. Okay, and so if it was Monday, then he said 2 days from now it's going to be Wednesday. In this case, we got that 3 to the power 47, that's congruent to negative 2 mod 7. So that's why we went 2 days back. So 3 to the power 47 days from now, it will be Monday. Does anyone have any questions about this? Was that explanation okay, Versano? Yeah, okay, good. Okay, now you can imagine if with this modular arithmetic mechanism that we're teaching you and the theorems that prove why this works, okay, you can imagine if it's that powerful for you to be able to do that just without a calculator, just with a little bit of mental arithmetic, you're able to calculate that. Imagine what the computers can do when we tell the computers about these theorems. Okay? So this, I think, is even more powerful, and this is actually the foundation towards how a lot of computers do calculations. Now, I do have one more problem on the in my slides. A bit of a more complicated problem, but this is a question from a previous exam on Math 135. So it's something that you should be able to do by the end of the course. And if you want to try it, you can try it in the class. And if you have any questions, you can ask me about it too. So I'm going to maybe, you can try this in the last 2 or 3 minutes of the class. And I'll also write some hints on the board as we're going. Okay, but if you try it on your own, that might also be a good idea. So 2 to the 4 is 5, well, 5 mod 11. 2 to the 4. So 16 mod 11, what's that? Louder? 5, yeah, good. Okay, so I'm giving you 2 to the 4 is 5 mod 11. I can also give you 3. What's 25 mod 11? 3. Okay, so you can use the fact that 2 to the 4 is 5 mod 11, 3 cubed is 5 mod 11, 5 squared is 3 mod 11. Three to the 33 is what we're going to do here. Five to the 55. Okay, now we can split up 2 to the 22, that's equal to 2 to the 4 times 5 plus 2. So that way we can use what we calculated there, 2 to the 4. 3 to the 33, this equals 3 cubed to the power 11. 5 to the 55, that equals 5 to the power 2 times 27 plus 1, right? So now if I have, here I have, the easiest one is 3 cubed to the power 11, right? So I have 3 cubed is congruent to 27 mod 11. I can raise each of these to the power 11. And then I have 5 to the power 11. So then I'm going to want to use what I did, what I had here, right? So, okay, so now that it's 4:50, then I thank you very much for your attention today, and I'm just asking you to think about this problem. We'll go over it in more detail on Friday. Okay, that was I wasn't actually intending for you to do that problem today. That was just something to look at before next class. Okay, did anyone have any questions today about any of the material today? Okay. Okay, I'll see everyone on Friday. Okay.